introduce Bowen for the fourth of his series of 5 lectures. The title of this is When Does I better get this right because he taught us lecture. I remember his line was injectivity makes sense or surjectivity makes sense, but you better get it right. So when does injectivity imply surjectivity? How's that? Did I get it right?
Yeah, that's right, yeah. So I'm going to talk about that mostly at the end of the talk because it's going to make more sense to mention a few other results before then and kind of work in that direction. Well, and just to kind of give more context. Okay, so what I'm writing down is something of a reminder of what I mentioned in a previous talk. So just to remind you, one of the kind of fundamental actions that I'm interested in is a Bernoulli shift, and it's given in the following way. We have a probability space, which it's helpful to have an example in mind and just think of K as a finite set, you know, if you just want to have an example in mind. Then gamma is acting on this probability space, which is just the product space. So it's just like we're just labeling elements of gamma with this alphabet K, and it's just like IID labels. Okay, and so it just acts by shifting the colors. And this is called the Bernoulli shift over gamma with this base space. And one of my results, well, is that if it happens to be a sofic group, and if 2 Bernoulli shifts are measurably conjugate, then the base entropies have to be the same. And so this generalizes Kolmogorov's result, which proved this when gamma equals the integers. Okay, okay. I mean, that's just review. So let me get to new things. Okay, so result of Sinai. Actually, I guess I'm not going to get to new things for a while because I want to present a little bit of motivation. So in the history of entropy theory, one of the big results after Kolmogorov's result was Sinai's factor theorem. And it says the following, that every ergodic transformation or action of the integers with positive entropy factors onto a Bernoulli shift. I'll just abbreviate as a B shift. Okay, I really think this is like one of the most important results in the, in the theory of entropy, because it tells you that, any transformation you can just think of as a Bernoulli shift and then a 0 entropy extension.
The same entropy?
Yes, that's true. You can give it, you can make the Bernoulli factor have the same entropy as the transformation. So I'll just write it this way, but okay. Just to mention it, I'm not going to say a whole lot about this result, but there's a result of Krieger, I guess it's 69 or 70, which says that if T is ergodic, so T is the transformation, and the entropy is bounded by log n, then there exists a generating partition let's call it P with at most n parts. So maybe I should remind you what this means. So T, right, is just a transformation from x to x. P is a partition of x. So here we have x, and we're cutting it up into n parts, or at most n parts. And to be generating means that the sigma algebra, so P is generating, means that the sigma algebra that's generated by P and the action is all Borel sets. up to measure 0, which we always ignore, sets of measure 0. Okay, so this is like saying, and I guess this is very useful, at least philosophically or psychologically, what does it mean to have entropy at most n? Well, it means that we can code it using at most n things per group element, n symbols. Okay. Now, another major result is due to Ornstein. So Bernoulli shifts over the integers are classified by entropy. So what I mean is that if you have two Bernoulli shifts over the integers, they're measurably conjugate if and only if they have the same entropy. And there's a lot more that can be said about this theorem and the things that came afterwards. And maybe I'll do that at the end of the talk if there's time. Okay, so what I want to do first is explain what happens when you replace the integers with an arbitrary group. That's what a lot of this talk is going to be about, maybe the first 30 or 40 minutes. And there's been some really stunning new developments, like in the last month. So I'm very excited. Okay, so first I will tell you about Theorem 4, how we've generalized that. Yeah, actually the way it's worked is that we generalize this one, and then this one, and then this one. So it's opposite of...
Titles are evolving.
yeah, that is why my title is evolving.
Occurring in the last few weeks.
That's, yes. Yeah, I want to talk about the things that I'm excited about, so I have to. Okay, so my theorem, I guess I'll call it Theorem 5, which is from 2012, says that basically Ornstein's theorem extends to arbitrary groups with some caveats, okay? Unfortunately, there is some cases that we can't completely handle. Actually, before I'll say my theorem, let me explain an earlier result due to Stepan. It also uses Ornstein and Weiss. And I guess this is from the 80s. Yeah, let's say 80s. Okay, if gamma contains an infinite amenable subgroup, such as the integers, then the same statement holds. Okay, so same conclusion as 4. Now, by entropy here, I just mean the Shannon entropy of the base. Because for an arbitrary group, we don't have any sofic entropy theory. We don't have any, we can't talk about the entropy of an action. But we can always talk about the entropy of the base space for a Bernoulli shift. Okay, so the way that this works, let's say that we contain a copy of the integers. So, here's my group, and I just consider it as, I just divide it up into cosets of this subgroup, which is a copy of the integers. Now, I have an isomorphism. Ornstein tells me that I have an isomorphism when I restrict to this copy of the integers. And so I can just apply that isomorphism now coset by coset. And I can build an isomorphism for the group. So this is a very easy proof. This is not like, it takes maybe a couple of paragraphs to say everything rigorously, but it's very easy.
Why is the entropy on that subset the same?
Because, okay, so we have gamma is acting on k gamma to the z, to the gamma. And I just think of this as giving a coloring of the group by elements in this finite set. And if I just restrict to my subgroup, that's just Bernoulli shift over my subgroup. It's not the same thing as saying, you know, now I'm going to restrict to my subgroup here. That's not what I'm doing. I'm restricting the colors.
The entropy is defined just as through the symbol.
Yes. Yeah. So I'm not really there's nothing particularly deep going on. It's maybe very useful to think about it in the special case when gamma is z squared. You know, the principle will be the exact same. You're just thinking, okay, on this copy of the integers, we see a bunch of symbols. Because of Ornstein, we know how to recode that into the new alphabet. And we can just do that on each layer. And it turns out you don't need normality or anything. OK, so my result from 2012 is essentially the same thing, except now I don't require anything on gamma. So gamma can be arbitrary. But there's only one unfortunate aspect. I need to require that both of these spaces are at least cardinality 3. That is, I can't allow just a set with just 2 atoms. Okay.
You seem to have skipped the analog of finite.
Yes. And that's on purpose because it's a harder result.
That starts with any system, not a Bernoulli shift. It shows that there's a factor.
Yes.
Well, this is just about Bernoulli shift. Okay.
Yes, that's right. Yeah. I will get back to Sinai, but it's a more difficult result and requires more work. So I would like to just kind of very briefly sketch the proof of this, because the tools that are used and kind of the philosophy also goes into the extension of this one, and to some extent the extension of this one. Although this is the easiest one, by the way, of all of the.
Do you know non-trivial examples of like Tarski monsters or something?
No. As far as I know, it's possible. We have no counterexamples. So it's an open question whether or not this restriction is necessary.
Yeah, what I meant is your theorem. So it's hard to construct groups that don't have infinite mutable subgroups.
Yes. Yeah.
I think an example.
Right.
Like examples, so
yeah.
Do you know of any other non-trivial examples to which your theorem applies?
No. Tarski monsters. It's got. Right. My theorem applies to these groups that where every proper subgroup is finite. Otherwise, it's already done.
I think he's asking you that they exist. I'm glad you pointed out they exist. I wouldn't have known.
Yeah, they exist. Due to Olshansky, right? Okay. Well, I'll explain the philosophy of this very briefly. What we have, suppose there's kind of 2 steps. Suppose that we are in the following nice situation. We have these 2 probability spaces, and they have the same entropy. That's the assumption. But suppose that they have a non-trivial common factor. And this is non-trivial, so it's not a 1-point space. Then I'll explain how the theorem goes in this special case. And then it turns out that you can always reduce to this case. OK. So in this case, what we can do is we can just put a gamma here. And these are factor maps now. These are gamma equivariant factors. And there's a result due to Zimmer. At least I think it's due to Zimmer. Maybe it's older. Which says that there exists a transformation of this space, automorphism, so a measure-preserving map, which is aperiodic, in fact, ergodic. And the orbits of T, every orbit of T is contained in an orbit of gamma. So you might be able to see what I'm doing now. I want to apply Stephan's trick. I want to take my group and say divide it up into copies of Z. But my group maybe doesn't contain Z. So I find a measurable copy of Z. That's what this is doing. It's finding a random copy of Z inside my group. And what's nice about it is that this random copy of Z, because it's in this common factor, it's basically, it exists inside this action and this action. And there's a relative version of Ornstein's theorem due to Tovino, which tells you that this system is going to be, well, I'm speaking too fast, so I'll say it a little bit more. So there exists a diagram now. We have this transformation, and we can lift it up to this space. There's a unique way to lift it so that it's taking, so that it's still within the gamma orbits. The orbits of this one are still within the gamma orbits. And Tovino's theorem gives us now, so it's Tovino's relative version of Ornstein's theorem. Implies that there exists an isomorphism. So between this transformation and the corresponding one over L, and that we have a commutative diagram here. So there's an isomorphism which commutes. And you can now apply this one sort of so-called coset by coset, even though we don't really have cosets here. What we've done is we've taken the orbit of gamma and we've divided it up into orbits of Z.
So what about how Zimmer makes that T?
Well, there's a...
I mean, that seems to be critical for him.
Yes, it is. It is. I mean, it's a great result. It's kind of the... I mean, as you were pointing out, you have these Tarski monsters in group theory, where where every element has proper order, but you've got a non-amenable group, maybe even a finitely generated group. The same thing cannot happen in the theory of orbit equivalence relations. That's what Zimmer proves. You always have an ergodic transformation. Yeah. I think I'll skip it. I haven't thought about it in a while. So I don't think I can, give you a 2 or 3 line explanation. But it's a general result about measured equivalence relations. You don't need anything about groups. Yeah, are there any questions? This is maybe a little bit, okay. Okay, so this is just kind of a brief sketch, but the main idea is that we're not going to reprove Ornstein's theorem at all. We're just going to use it basically as a black box. Well, really a relative version as a black box. And we need some kind of, well, maybe I should tell you the last step. As it turns out, if these two are arbitrary, then there always exists a space in between where you have common factors. So if maybe you didn't, maybe you start off with a K kappa and an L lambda that don't have a common factor. Well, it turns out you can always build a third space so that now these three all have the same entropy and you have non-trivial common factors. But you can only do this when K has at least 2 atoms and when L has at least 2 atoms.
Is that coming from some combinatorics at some point?
Yeah, it's very easy. You just take the largest atom of K and the smallest one of L. And so that gives you 2 numbers to build this probability space, then you just fill it out the rest. So your factor is going to be, these are going to be 2-point spaces. It's just a little bit of, it's just an exercise. But of course, it's not going to work if this only has 2 atoms, because then it doesn't have any non-trivial factors. So we're kind of stuck there. Okay, so I'll tell you about the generalizations of Krieger and Sinai, but there we're going to need some real entropy theory. We can't just say, use the Shannon entropy of the base. That's not going to work. Okay. So just for motivation, I'll remind you of the following. Suppose that we have a transformation, measure-preserving map, and we have a generating partition, which you remember means that the sigma algebra generated by this partition in the transformation is everything. Then it's not difficult to prove that the entropy is bounded by the Shannon entropy of the partition. The Shannon entropy of the partition is, it's something that only depends on the partition, not the transformation at all. So it's just a finite calculation. Okay, so what we can do now is we say, well, we should take the infimum of the right-hand side over all generating partitions. Okay, and so this is what we call the Rocklin entropy. So the Rocklin entropy, more generally, Rocklin entropy of T is just the infimum of the Shannon entropies of partitions over all generating partitions. Now, what it means to be generating depends on T. So this does depend on T, but is it clear? This is like a really crucial definition. I know it's simple, but it's like really crucial. Okay, so we can extend this to arbitrary group actions. I want to keep, I guess, Sinai and Krieger, so I can go here.
That's the same as the
yes.
Just another way, so it's an equivalent definition for Z?
Yes, as it turns out, well, assuming ergodicity.
Yeah.
So if T is ergodic.
It's not a different entropy, it's just a theorem that this is another way to define it.
Yes, and yes, that's a theorem due to Rocklin in the 60s. Okay, so we can make the following definition. We define the Rocklin entropy of, now we have an arbitrary group acting on a probability space as the infimum of Shannon entropies of partitions over all partitions that are generating. So that means that the sigma algebra generated by P and the group action is everything.
There is no sofic.
Yes, there's no sophicity needed. This is kind of the part of the beauty of it. I mean, it's a really, natural definition. Okay. Okay, well, obviously it's an invariant. I mean, there's no choices. So it's a measure conjugacy invariant. Now, for sofic, if your group happens to be sofic, then sofic entropy turns out to be a lower bound for Rocklin entropy. This is just almost, you can prove this directly from the definition.
Sofic entropy is dependent on the on a further notion.
Yes, yes.
So for any of those?
Yes. Yeah. So for any sofic approximation, you can define something called sofic entropy. And it's just immediate from the definition that you get this bound. And in some cases, you can check that they're equal. So, for example, for Bernoulli shifts over sofic groups, we happen to know that they're equal. You know, these are, we get equality. That's an equality. But we don't know, you know, it's very difficult to compute Rocklin entropy in general because this is the only lower bound that we know about.
Take the supremum over all approximations and expect it to be.
Yeah, yeah, exactly. Okay, conjecturally, right. Yeah, okay, so conjecturally, sofic entropy is equal to Rocklin entropy whenever this one is not minus infinity. So unfortunately, this one can sometimes be minus infinity. We have examples. But conjecturally, except for this case, these two are equal.
What is the existence? P is finite partition?
It could be an uncountable, I mean, a countable partition, or even an uncountable one. I mean, because then you're just getting infinity, so it's not.
So the
Yeah.
existence.
Well, we're always going to be assuming ergodicity, and there's a theorem that there's always a countable partition. Though you don't necessarily have a finite partition always, because the entropy could be infinite. You know, that's. Okay, let me just mention, if this thing is true, if this conjecture is true, then you know this problem about L2 Betti numbers mod p. Well, if this, you need a slightly stronger, like a relative notion of this. There's a relative version as well, but I won't say what that is. But if this is true and the relative version is true, then what you get is that L2 Betti numbers mod p exist. You know, the limit that defines them is that actually exists. And it's going to be given by, you know, it can be interpreted as a Rocklin entropy notion. This thing also kind of comes up in statistical mechanics models, but I'm not going to mention that because, you know, in statistical mechanics, you often look at large but finite graphs, which are locally tree-like, and you have some kind of model like the Ising model, and you're looking at the partition function, and you want to say, well, as my sequence of graphs gets larger and larger and larger, and Benyamini-Schramm converges to the tree, then the asymptotics of the partition function shouldn't depend really on the graph. It should only depend on the limiting object. And this would confirm that, that conjecture. Okay. Okay, so I guess this is theorem, I don't know, 6 or 7 now. Due to Seward, Brandon Seward, in his PhD thesis that was finished in the spring, generalized Krieger's theorem. So for R gamma. So what he shows is that.
This is a guy from Michigan.
Yeah.
You go to New York. You try to.
No, he went to, well, he's in Jerusalem for a year and then in New York. Yeah. So, okay, he extends this to arbitrary gamma where you replace this entropy with Rocklin entropy. But he actually proves a stronger result as well. That instead of saying, well, there exists this generating partition P and it has at most n parts, you can in fact specify the distribution of P as long as it satisfies the necessary condition that its Shannon entropy is bigger than this. So I guess we could do it like this. Surd. So we need ergodicity, although there is a non-ergodic version on the way. You want to say that the Rocklin entropy is bounded by the Shannon entropy of some probability vector. Then there exists a generating partition with, well, the distribution of P equal to this probability vector. So if it equals this, then what we have is that the measure of Pi is equal to little pi. So, okay. I'm not going to say very much about that result. The proof's a bit, well, for the sake of time, at least. The proof's a bit difficult, but I don't want to say very much about it. The Theorem 8 is also due to Seward, proved last month, which generalizes Sinai's theorem. So with using Rocklin entropy. So if the Rocklin entropy of an ergodic action is positive, then there exists a Bernoulli factor. And in fact, well, there is a notion of relative Rocklin entropy. I'll skip that, but you can imagine what it is. Yes, but you see, saying it that way is not very pleasant, because the problem is with a non-amenable group, you can very easily have an action with Rocklin entropy 0 that factors onto an action with Rocklin entropy infinity. And so, and conjecturally, for a non-amenable group,
that you wanted out of entropy or failing for Rocklin. You had this factor can't have more entropy than the thing itself.
For a non-amenable group, it can.
I thought yours.
Well, for Bernoulli shifts, okay, this is just isomorphism. If you have two Bernoulli shifts that are isomorphic.
Didn't you demand some properties of entropy, which you were defining your entropy? One of them that a factor.
No. No, entropy can increase under a factor map. In the case of whenever you have non-embeddability, it's a condition that you can't get away with, can't get away from. And in fact, so what I showed right last time was that the Bernoulli, the full 2 shift over the free group factors onto the Bernoulli to the full 4 shift over the free group. But in fact, for the free group, all of the Bernoulli shifts factor onto each other. That's a result that I showed, but it basically just uses Ornstein and Weiss. You know, basically just uses this one example of the 2 shift factoring onto the 4 shift, and you kind of massage this example a lot. And you can go even further, and you can say, okay, so maybe I should mention this. So a result of mine is that if gamma contains a rank 2 free group, then all Bernoulli shifts factor onto each other. And there's a result of Karen Ball, which, well, it can be improved a little bit, but it says now if gamma is non-amenable, any non-amenable group, then there exists, well, there exists some number r, which is finite, maybe 0, such that if the entropy of the base space is bigger than R, then this Bernoulli shift factors onto all Bernoulli shifts. Okay, this isn't quite her result. This is my improvement of her result, but it's basically. Conjecturally, R should be 0. You really shouldn't, all Bernoulli shifts should just factor onto all Bernoulli shifts for a non-amenable group. And so that's why, okay, there exists a Bernoulli factor, and it should be the truth that you can factor onto any Bernoulli shift. But there is a notion of relative Rocklin entropy, and what he shows is that you can choose this Bernoulli factor so that the relative Rocklin entropy is 0. And so that's a notion of maximal that is very useful. Yeah. Yeah, actually, maybe I should pause. I feel like. Pause for a moment. Questions?
At some point, you might review what it's not a beatable well. All the counterintuitive things.
Yeah. Okay. Well, yes. Yes. Okay. Yeah. Let me do that. I'll get back to Seward's theorem in a moment. Yeah, okay, here's a very quick review. So this is the free group. And if you have 0, 1 to the free group, it maps onto 0, 1 times 0, 1 to the free group. In the following way, we just put our, you just think of IID labels here on the vertices. And we just add this one to the one north and add this one to the one east. We do that everywhere. So this shows that the 2 shift factors onto the 4 shift. So entropy seems to increase. But you can bootstrap this. You can say, OK, once we've done this, let's ignore this factor and apply the same map to this factor. So we can get the 2 shift to factor onto the 8 shift. And we can keep going, and we can get the 2 shift to factor onto the full infinite entropy shift. So we can get it after a little while onto a Cantor set with, with the usual Cantor measure.
Okay, this is bad stuff. What was good from the last lecture was in the situation, the entropy was in terms of isomorphism.
Yes, okay. These are not isomorphic, but one does factor onto each other. It's a it's a subtle thing. Okay. Right. Yes, okay. Yeah, I should mention maybe as a, just to also explain how strange this is. Once you show that all of the Bernoulli shifts for the free group factor onto each other, it follows that you can take an inverse limit of Bernoulli shifts, and you get a new system which has 0 Rocklin entropy, and yet it factors onto all Bernoulli shifts. And it's not Bernoulli itself, of course. It can't be. It has it has 0 Rocklin entropy. It's not even a factor of a Bernoulli shift. So just to mention a kind of parenthetical remark, Ornstein proved, and Ornstein and co-authors proved that factors, inverse limits, and d-bar limits of Bernoulli shifts are Bernoulli.
for Z?
Yes. We now have counterexamples to all three for non-amenable groups. Popa showed that if you have any property T group, so if gamma has property T, so Popa has an example where gamma has property T, and you consider gamma acting on Z mod PZ with, say, uniform measure. And OK, that's just a Bernoulli shift. But now what we do, let me write it this way. So it's Z mod PZ to the gamma. That's just a Bernoulli shift. But now we factor out by the action of Z mod PZ. And you can show that this is not a Bernoulli shift anymore. It's a factor of a Bernoulli shift, but it's not a Bernoulli shift. And it's because he computes the cohomology group and shows that it's not the same as a cohomology group of a Bernoulli shift. So it's not even measure equivalent to a Bernoulli shift. And I just showed you that inverse limits are not. And the same example shows you that D-bar limits are not. Gives you a counterexample. So this is actually really tough. I mean, the reason why is because one of the reasons why Ornstein's machine is so powerful, he gives you this criterion called very weak Bernoulli. And it has the following properties that if you have a system and it has a partition which is very weak Bernoulli, then all partitions are very weak Bernoulli. And in fact, the system is measurably conjugate to a Bernoulli shift. And from that, he derives these properties. But we don't have anything like that in the non-amenable world yet. I mean, there's no. I mean, probably there isn't because we have these counterexamples. So we don't know what to do. OK, so I thought maybe I'd say a few words about this, but for the sake of time and because I want to tell you some other really interesting theorems, I'll just say a few words. The proof is a lot like my proof in the sense that what it does is it says, OK, we have this original action. We take a factor which has small entropy, but so that the action is still free. And it turns out that that's possible to do. That's a non-trivial result of Seward and Tucker job. Then using that, they build, they find a transformation. So they find an automorphism. But this time, this automorphism is not ergodic. And in fact, it's important that it's not ergodic. It's in fact very far from ergodic. But you can still lift it. And I guess in a few words, it's going to be hard to say much. But he does use a relative version of Sinai's theorem. He uses a notion that we call percolation entropy, which is you have this percolation process, and so you've got like a random subset of your group, and you condition on seeing what's going on in this random subset. You see all the colors in the random subset, and then you ask what's the entropy at the identity, and you take the expected value of that, and that turns out to be an upper bound for Rocklin entropy. And whenever it's positive, you can use the relative Sinai theorem with this T tilde to push everything through. Okay. Are there any questions? OK. OK, so now I can get to, I can almost get to injectivity and surjectivity. Almost. Let me say a few more things. OK. So I'll start off with a definition. If you have an arbitrary group, you very well might ask, does it have an action with positive Rocklin entropy? This is maybe a weird question. It seems like there has to be one, at least. The Bernoulli shifts should have positive Rocklin entropy.
Gamma's infinite.
Gamma is infinite. At least there should be one action with positive Rocklin entropy, you know, like Bernoulli shifts. But because we have no way of getting lower bounds except when the group is sofic, we don't know. So we make a definition, which is this is the soup of Rocklin entropies over all actions which are, let's say, free, ergodic, and there's one other criterion which is a little weird. We also require that this Rocklin entropy is finite. Okay. So just the soup, you know, so for any sofic group, this is infinity. But there might be non-sofic groups lurking around. We don't know. Okay. This is due to Seward. I'm not motivating this very well, but so I want to tell you there are some very nice corollaries. But an interesting result is the following. You consider the Rocklin entropy of a Bernoulli shift. And he proves that for any group, this is either the Rocklin entropy of the base, or it's this soup. If there's time, I'll say a few words about the proof. There's a lot of ingredients to it, but it's okay. Okay, so here's one corollary. If this soup of Rocklin entropies is infinity, then the following is true. If we have two Bernoulli shifts, which are measurably conjugate, then they have to have the same base entropy. So we have the Kolmogorov theorem. And so this is, you know, so this is more general than just saying the group is sofic, because, yeah. Okay. And another one, if this is true, well, then Gottschalk's surjectivity conjecture holds. And so I should remind you what that is. For the group. Yeah. There's a few more things that we can say that are very interesting, I think. Okay. So what is this? Yeah, if every group is sofic, then. If every group is sofic, then yeah, sure. But what this tells you, I mean, philosophically, I think what this tells you is that if there is an entropy theory for all groups, it has to be Rocklin entropy theory. In some sense, you know, maybe there's more than one entropy theory, but if there's only one, then it has to be Rocklin entropy. Okay, so does injectivity imply surjectivity? You know, okay, when you have a map from a finite set to itself, the answer is yes. What can you say in other conditions, circumstances? This was Gromov's question. He mentioned a bunch of things in his paper, like if you have an algebraic variety and it has a map from it to itself, and it's a regular map, then if it's surjective, it must be surjective. If it's injective, it must be surjective. Yeah.
Since you taught us so well.
Okay, so Gottschalk's conjecture is the following. We consider, so it's the following statement, that if A here is a finite set, and we have a map from functions from gamma to A into functions from gamma to A. So A is a finite alphabet that is continuous, compact open topology, say, gamma equivariant, and injective, then it is surjective.
So he actually conjectured this for any gamma. That was,
yeah.
And Gromov proved it for sofic.
Right.
And somebody gave a proof using your entropy also for sofic.
Right. Yeah. Yeah. Okay, so the way that this goes, so I guess part one is pretty much immediate from this. You know, if this is infinity, then you're just getting here. So part two, well, you just put the uniform measure on A. So, okay, and then you have a measure on A to the gamma. You have this Bernoulli shift. You push it forward. If it's injective, well, the Rocklin entropy has to stay the same. But it's not hard to check that if it's...
So he solved this problem. Okay, I didn't get my head around that.
Yeah.
I was saying he solved the 4 groups.
Well, you have to assume this. You have to assume that this Rocklin entropy is, the soup of Rocklin entropies is infinite.
Your ifs are too many ifs. Okay. So he still has to, okay. So,
yeah.
But then he, in particular, he's got a new treatment of Gromov's.
Right. Yeah.
Well, it's close to yours.
Right. Yeah. So if this is infinite, then it holds. And the argument is similar. You just have the Rocklin entropy of the Bernoulli shift on this one. You push it forward. If it's injective but not surjective, then you get a contradiction because it's not hard to show that if it's not surjective, then the entropy has to be strictly less than log of the cardinality of A.
What was the condition on gamma?
It's assuming this H gamma is, if H is infinite.
It's assuming that the
arbitrarily large, the Rocklin entropy.
But that was fixed. What do you think that
so,
the conditions is large?
okay, so I'm just assuming.
So look at the definition.
I'm just assuming that if we take the soup over all Rocklin entropies over all actions that don't have anything to do with Bernoulli shifts necessarily, just all actions.
Then you can make it arbitrarily large.
Yeah, can you make it arbitrarily large? And I guess if I have one more minute, I'll tell you another very interesting result. So you might wonder, well, what about, if we have a group and we modify it in some way, how does this thing change? And what he shows is that, for example, if you take gamma and you take the direct product with, well, suppose that the infimum of Rocklin entropies is finite. Then if you take gamma and you take its direct product with, let's say, the countable sum of z mod 2z's. There are many other groups that you could put here, but then this is going to be 0. And because this is 0, then in fact the Rocklin entropy of all actions of this group has to be 0. And so what that tells you in particular is that, for example, if you take the Rocklin entropy of this group acting on, your most complicated action, that you might think, well, you take the unit interval with Lebesgue measure, and let's just put gamma prime here. So this is gamma prime. So you can just look at this Bernoulli shift. This Bernoulli shift should have infinite entropy, but under this condition, it's going to have 0 entropy. Which is really surprising because this, it would be very surprising if this even has a finite generating partition. There shouldn't be any. Okay, so to put it another way, if you can show that for every countable group, so conclusion, if for all countable gamma, this action does not admit a finite generating partition, Gottschalk's conjecture is true. Yeah, Gottschalk's conjecture holds. And in fact, you have classification of Bernoulli shifts for all groups. And this is something that when you think about it, it's like, how could you possibly construct a weird group that, where this thing would have a finite generating partition? It seems impossible. But there's no techniques to show that other than entropy theory. So at this point, we're kind of stuck. Well, I'm stuck. Maybe somebody else has it.
Did Gromov have a generalization that applied to more general, like transformations between subshifts of finite type or something? Applies surjectively? Or is that open?
He might have. So let's see. I mean, in order to show that, what you would want.
Assuming sofic.
What you would want is some kind of statement that your subshift of finite type admits a unique measure of maximal entropy, or I would think something like that. Otherwise, or maybe that all measures of maximal entropy are fully supported. Then you could run the same argument. And I don't know. I've never thought about that, so I'm not sure what to say. That seems plausible, but. At least for amenable groups, that's got to be true, for.
Is there a belief that everything is sofic? You seem to say that earlier. Maybe, surely that's the way to proceed. Or is this an attempt to actually prove that eventually?
Yeah, well.
Is that a standard conjecture?
Yeah, it is. So, I mean, most people that I've spoken with think there must be a non-sofic group. It's just, how can you? Yeah.
Not every.
Right.
Finitely generated countable doesn't help.
Right, yeah. It doesn't help because every subgroup of a sofic group is sofic. So if there's a.
Finitely presented doesn't help.
No.
So they are groups we're supposed to worry about. Okay.
Yeah. Right. So, yeah, no, I mean, what I think that this does is it just kind of emphasizes that Rocklin entropy is a...
Is there a sufficient condition for sofic, standard sufficient condition?
Now, this we don't know. I mean, this is, it seems reasonable that maybe Gottschalk's conjecture implies, the truth of Gottschalk's conjecture should imply soficity or something like that. But anyway, I don't want to go there because I don't know. It's very speculative.
This definition, I'm still confused. Like if gamma is free groups,
Sure.
This is
This is infinite.
infinite, or like if I give you a finitely generated group containing that, that would be infinite.
This we don't.
Offering a subgroup thing.
No, unfortunately, yeah, it doesn't go to supergroups, it goes to subgroups. So, like, okay, so if gamma is linear, then this is going, or sofic, then this will be infinite. But if you have a group which is contained in a group for which this is infinite, then your original group is infinite. It doesn't go the other way, yeah. Yeah, okay. Yeah. So.
And how about sort of a random, just talking about random groups? Somewhere if you make these random Gromov groups.
Yeah, I don't think anybody knows. Yeah, in fact, I've talked with some experts on this, and they don't know. Yeah. It's not known if the Berger-Moses groups are sofic, for example. And those are already very concrete. I should mention one thing, maybe.
So that's like the first test case.
Yeah, yeah, sure. So in general, if you take a free product of two free groups, amalgamated over some free subgroup, we don't know if that's sofic. If this is an amenable group, then it's sofic for sure. But if it's a non-amenable group, we don't know. So that's.
So people believe that these are not sofic?
People, yeah. Well, I don't know about the Berger-Moses groups, but in general, it's just a general feeling that, it would be too deep of a theorem to say that all groups are sofic. This is, Gromov's dictum that, all statements about, if you have a statement about all groups, it must be either trivial or false. So, since this would be a non-trivial statement, it has to be false, yeah.
We haven't seen, it's like you haven't seen the bad guys yet.
That's not a quasi-symmetry variant. It's soficity.
No, well, it's not known, of course, because if all groups are sofic, then it is. But no, it's not even known to be a measure equivalence invariant, which would tell you that if it was true, that would tell you that the Berger-Moses groups are sofic.
Quasi-symmetry.
Yeah. Yeah, I should maybe mention one of the things that I got from Seward's theorem is that if you have any non-amenable group, so if gamma is non-amenable and you have an arbitrary action, then there always exists an extension which has Rocklin entropy 0. So you really have strong failure of monotonicity. Seward had earlier proved kind of a weaker version that you could always get the Rocklin entropy of this to be bounded by some function of gamma, of the group, but you can actually get it down to 0. Yeah.
His paper's on the archive.
Yeah, yeah.
And what's the title of your last talk? And let's remind ourselves when it is. So it's this Friday, a week, I believe, back to 1:30.
Yes, and
The last talk had no title, I don't think.
that's right. I was going to ask you what you wanted to hear. Or I can ask the audience.
He has an email. You can send in what you want to hear. Proof of anything. So you will respond to any requests.
Yeah, I'll respond to requests. Absolutely.